Welcome. In this lecture, we will discuss Newtonian gravity, the inverse square law, weightlessness, and ocean tides. Legend has it that Isaac Newton was sitting under an apple tree when the idea struck him that what pulls apples from trees is the same force that keeps the moon circling the Earth. This leads us to the Newtonian synthesis. The physical laws governing celestial bodies are the same laws governing terrestrial bodies. This synthesis provided hope that other natural phenomena followed universal laws, and this ushered in the Age of Enlightenment. The force of gravity is proportional to the mass of the interacting bodies and inversely proportional to the distance between them. Mathematically, this is written like this: F is proportional to m1 times m2 divided by r squared. In the textbook, r is written as d, but both denote distance. Force of gravity is proportional to the mass, which just means that the larger the masses are, the greater the masses, I should say, the greater the force is. But the gravitational force is inversely proportional to the distance, meaning that the further away you are, the weaker the force is. If we want to make this proportionality statement into an equality, we must put a constant of proportionality here. Here I've written it as alpha, but in the context of universal gravity, instead of writing alpha, the symbol that is often used is capital G. And this capital G is known as the universal gravitational constant. Now to find the universal gravitational constant, because it's not just given, someone had to actually find this experimentally, we take the equation and we isolate capital G. Newton was not able to measure G. Henry Cavendish first measured G 70 years after Newton's death. Philip von Jolly measured G more simply and more accurately using what I'm going to show here. Of course, I'm showing it in a very simplified form. Let's say we have a scale, and on the left side is mass 1. On the right side is some amount of weight that allows the scale to be balanced. A large mass is rolled in, and the distance between the two masses is r. Well, m2, because it has so much mass, pulls down on m1. Therefore, the scale is no longer balanced. So what do you have to do? You have to add more weight on the right-hand side, and this additional weight, just the weight that's added to rebalance the scale, is considered to be F, the F in our equation. Now we have everything we need to know. We have F, we have m1, m2, and r. Now we can calculate G, and it has been calculated as 6.67 times 10 to the negative 11 Newton meter squared over kilogram squared. This is a very small value, very, very small value. This indicates that gravity is an extraordinarily weak force. It's the weakest of the four fundamental forces. In summary, Newtonian gravity is the magnitude of the gravitational force between two masses m1 and m2. A distance r apart is simply written as F equals G times m1 times m2 divided by r squared. And that gravitational constant, that capital G, not to be confused with lowercase g that we've used in this course. That capital G has this 6.67 value, very, very small. Now let's take a brief aside into the gravitational field. Now notice that I've rewritten, instead of using m1 and m2, I'm using lowercase m to denote the rocket's mass and capital M to denote the Earth's mass. Now I'm doing this for a very specific reason. Let's rearrange this equation. So now the lowercase m is outside, and this product of g times m times 1 over r squared, that is what we've seen before as lowercase g. So that lowercase g, which I've called the gravitational field, is exactly that. It's the gravitational field of the Earth. And so the weight, as we've seen it written before, is this: m times capital G times capital M, which is the mass of the Earth, divided by r squared, is the weight. We can rewrite this as mg, knowing that little g is just the product of those things within the gray outlined box. So the gravitational field is the field that interacts with other masses that produces the forces on those masses. So the field produced by the Earth interacts with the mass of the rocket, producing a gravitational force on that rocket. The gravitational force on you is due to the gravitational field of the Earth interacting with the mass of your body, the mass of the rocket, the mass of the baseball you throw, the mass of the plane flying overhead, all of that. Now let's talk about the special relationship, the inverse square law, the fact that the force of gravity is inversely proportional to the distance squared. So what happens if you double the distance between two objects? So instead of r, you have 2r. Well, I plug in 2r in the denominator, but then that leaves us wondering, well, what do I have to put on the left-hand side now? What's this question mark? What should that question mark be to maintain the same relationship we showed on previous slides? Well, on the right-hand side in the denominator, let's distribute the square. So we get 2 squared, r squared in the denominator. 2 squared is simply 4. That means that our question mark is simply, well, 4 in the denominator. Now we can pull that out as 1 over 4. This means that when you double the distance between objects, the force becomes 1/4 of the original force. What if you triple the distance? So instead of being at some random distance r, you're now at 3 times that original distance. Well, let's go through the same process. Plug in 3r, distribute the square, 3 squared becomes 9, therefore the question mark becomes 1 over 9, and the force becomes 1/9 of what it was. So if you triple the distance, the new force acting on the objects is now 1/9 of what it was initially. Last example, what if you quadruple the distance? You go from r to 4r. Well, same deal. You plug in 4r in the denominator, distribute the square, 4 squared is 16. The question mark becomes now 1 over 16. You pull that 1 over 16 out, and now we see that when you quadruple the distance between two objects, the new gravitational force is now 1/16 of the original gravitational force. This can be shown in a different way using the picture of a spray paint can. So a can of spray paint will spray, well, paint. And the closer you are to whatever you're spraying, the thicker the coat will be. So let's say you're very, very close. You're 1 meter away. And so you get some thickness, some amount of thickness on this single pane. Well, if you're 2 meters away, the spray will reach over a larger area. So let's say it can hit 4 of these panes. But therefore the thickness on each pane will only be 1/4 of the thickness when the panes were closer. If you go to 3 meters, now there's 9 panes to cover with the same amount of paint. So that means each pane will only have 1/9 of the original thickness of paint. And so on. 4 meters away, now each of the 16 panes will have 1/16 of the thickness of paint. Graphically, if you take the Earth, you can draw our axes, force on the y-axis, distance on the x-axis, take this as the surface of the Earth's dotted line. Away from the surface of the Earth, the force follows the inverse square relation. The further you are away, the more dramatic the fall off. So the force gets weaker. The force of gravity gets weaker the further you get. Now inside the Earth, the relationship is a little different. It's a linear relationship. We won't be talking about that, but I simply want to mention it. The book mentions it in the section on the gravitational field. I will simply mention it here, and then we'll move on from this. What I want to emphasize is the inverse square relationship. How does this affect us? Well, if you step on a scale, let's say a child weighs, at sea level, a child weighs 300 newtons, just as an example. If that same child were to climb up to Mount Everest and stand on a scale there, the child will weigh 299 newtons. Now, why is that? Because the child is now further away from the center of Earth, so the gravitational tug is weaker. Now, it's important to note that the gravitational force gets weaker the further you are away. It never reaches 0, though. It approaches 0, but the gravitational field extends throughout all of space, so it doesn't actually go to 0. Example, the gravitational force between two objects is 12 newtons. If the distance between the two objects is doubled, the gravitational force between them is A, 24 newtons, B, 10 newtons, C, 6 newtons, D, 3 newtons. How do we do this? Let's write our initial. Force initial is G m1 m2 over r squared. Well, we're not really given a lot of information, but we are told that our initial force is 12 newtons. We want to know what the final force is. The final force is, well, the same masses, but now our distance is doubled, so we simply put 2r there in the denominator. And we've done this already many times before. We now distribute the square. So we have 2 squared r squared. 2 squared is 4. We can pull that 4 out, so we get 1 over 4, and we see that this mess of variables is the same as the upper mess of variables initially, which is simply the initial force. So we're going to replace this with initial force, and we're given the value of the initial force is 12 newtons. So now we plug that in, and we get a value of 3 newtons. So we see that when you double the distance, the output force is now 1/4 of what it was. Weightlessness. Now I have to say right off the bat that I disagree with the book's definition of weight, or at least my understanding of the book's definition of weight. I'm defining weight to be the gravitational force. So m times the gravitational field, mg. And This N, if you're stepping on this scale, this N is your upward force, the support force. This is what produces the sensation of weight. If you weren't stepping on anything, you wouldn't sense that you weighed anything. But I must make a distinction between weight and the sensation of weight. Let's look at an example. Let's say you're in an elevator and you're moving up or down with constant velocity. You're not accelerating. So the value that the scale reads, if you're standing on a scale in the elevator, it will read what your actual weight is. And you will feel that as being normal. That may not make sense. We'll talk about what I mean by feel in a moment. Starting here. Let's say the elevator accelerates upward. This is what would happen if you stepped into an elevator and let's say you're on the bottom floor and you want to go to the top floor. As soon as the elevator begins, you go from zero velocity to some non-zero velocity, meaning you accelerate. Well, you feel like you're being pushed into the ground. So in that moment, during the acceleration, you feel as if you weigh more because you experience an inertial force. So you experience a greater sensation of weight. Doesn't mean you weigh more, it just means that your sense of it is greater. What if you're going down? So let's say you start at the top floor instead, and you want to go to the bottom floor. Well now, when you accelerate downward, you feel an upward inertial force. So you feel a bit lighter here because you're no longer being pressed as powerfully into the ground. So you have a lesser sensation of weight. And to go to the logical and dramatic end, if the rope snaps, you're accelerating perfectly downward at gravitational acceleration, you don't really feel your weight anymore. You're in free fall. You're not pressed up against anything, so you have no sensation of weight. Astronauts experience this. They have no sensation of weight because they're not being pushed against anything. Does that mean they don't have weight? Of course not. They still have mass, they still have acceleration, gravitational acceleration. They still have a weight. They just don't feel the weight because nothing is pushing against them. The sensation of weight is distinct from having weight because weight is just a force applied to you, has nothing to do with what you feel. The fact of the force is completely distinct from the feeling. Ocean tides. Now we know there are low tides and there are high tides. There are actually 2 high tides per day and 2 low tides per day. What causes them? Well, Newton understood that tides are caused by differences in the gravitational pull between the moon and the earth on opposite sides of the earth. The pull is stronger on the side of the earth nearest the moon and weaker on the side of the earth farthest from the moon. So the earth has 2 bulges. One bulge mostly to the gravitational force. But there's more than just a single bulge, as you can tell. There are 2 bulges, so what's up with that? What causes the bulge on the side of the Earth that is opposite the moon? Well, the centrifugal force does actually, which may seem a bit odd, but remember that the Earth is not a static object. It's also moving through space. And both the moon and the Earth actually orbit the center of mass of their system. So this center of mass that has been pointed out here is the center of mass of the Earth-Moon system. So it's the average position of the mass of the Earth and the moon. And because they orbit this, the centrifugal force is produced. Let's take a look from a different perspective. The Earth and the moon both rotate around the center of mass. So both the Earth and the moon experience the centrifugal force, but we're focusing on specifically the centrifugal force produced on the Earth. And that centrifugal force is what yields that second bulge. So one bulge is primarily produced by the gravitational force, and the other bulge is produced by the centrifugal force. What about the Earth and the Sun? Well, same deal. The Sun pulls more strongly on one side of the Earth than the other, so that creates one bulge. And just as with the Earth-Moon system, the Earth-Sun system has a center of mass. Now, because the Sun is so massive, the center of mass of the Earth-Sun system is actually inside of the Sun, and because they both orbit this point, the Earth experiences a centrifugal force. But notice that I've made the bulges smaller here, and that is because the gravitational force difference between the nearer and farther sides is smaller than that of the difference produced by the moon on the Earth. Now, I'm not saying that the absolute gravitational force is smaller as produced by the Sun, but the difference between the nearest and farthest sides of the Earth due to the pull of the Sun is smaller than the difference due to the moon. And I'll show that on the next slide. So here's the Earth and the moon. Let's draw our axes, force and distance. Let's draw the gravitational force plot, and let's draw the force from the moon on the Earth on the side of the Earth nearest the moon. So it's some value, and then the force of the moon on the Earth on the farther side of the Earth. This is the difference in the gravitational force due to the moon. So the difference of the force from the nearest side to the farthest side is some value. I don't care about the value here, not specifically. I care about the difference between the poles versus nearer side and farther side. Now look at how this difference compares to the difference produced by the sun. And this is not even to scale. The difference would be much smaller than I've even shown here. So the point is, the tidal effect by the moon, if I'll go back, by the moon on the Earth is larger than the tidal effect of the sun on the Earth, because the difference, and I'll go back again, in the gravitational force from the moon is larger than the difference in the gravitational force by the sun. But they're both doing something, so they can actually work together. They can actually produce a compounding effect. We have the effect, the tidal effect of the moon, and the tidal effect of the sun. And when they're oriented like this, where we have the sun, the moon, and the earth in a straight line relative to each other, this produces a complementary effect, meaning that there are higher high tides and lower low tides. These are known as spring tides. Conversely, if we have conflicting effects, so the moon is pulling one way and the sun is pulling another way, well, that means the high tides are not as high and the low tides are not as low. And these are known as neap tides. Summary: we discussed Newtonian gravity, the inverse square law, weightlessness, and ocean tides. I'll see you next time.